Hello everyone, welcome to today's seminar. It is my great pleasure to start the seminar series this year with our great guest, Professor Barry Rand. Barry is jointly appointed between the Department of Electrical and Computer Engineering as well as the Andlinger Center for Energy and the Environment at Princeton University. Prior to Princeton, he was at IMEC, where he was a principal scientist researching the understanding, optimization, manufacturability of thin-film solar cells. Professor Rand's research is at the interface of electrical engineering, material science, applied physics, and chemistry, covering electronic and optoelectronic thin films and devices. He's authored more than 200 journal publications, holds 25 U.S. patents, and has received several awards, amongst which are the 3M Non-Tenured Faculty Award, DuPont Young Professor Award, DARPA Young Faculty Award, ONR Young Investigator Program Award, and the Gordon and Betty Moore Foundation Experimental Physics Investigators Initiative Award. So before I hand it over to Barry, just a reminder for our audience, if you're here in person, please feel free to raise your hand to ask your questions. And those who are joining us online, you can type your questions through the Q&A feature of the Zoom webinar, and I can help moderate the questions for you. So with that, welcome to MIT. Thank you for coming, and we're excited to listen to your talk.
Thank you, Farnaz. Oh, thank you for eating into my 40 minutes. So I'm going to tell you today about some of the work that's going on in my lab regarding interface reactions between some medium and halide perovskites, and in a way to try to understand two different phenomena. One is the phenomenon of degradation, how these materials break down over time, and the other one is to understand doping and see if we are in fact capable of either P or N-type doping of these media, meaning controlling the electron or hole population of these semiconductors. So let me start with a brief introduction for those that might not be familiar with metal halide perovskites. I like to view them as, this is the unit cell, the sort of tetragonal system here, but I like to view them as a series of these metal, in this case either lead or tin at the center, octahedra with 6 of these apical iodides or halides in general on the outskirts of it. And then you have this A site, which is positively charged, which sort of has the right size to scaffold this system and also charge balance it to hold it together in this 3-dimensional octahedral corner sharing sort of mantra. And by changing the halide or changing the metal, you can actually sweep the system's response from the blue all the way out to the near infrared. And they're direct bandgap semiconductors, so they're interesting for all types of optoelectronic devices. Here's some examples of LEDs and lasers. But the real success story has been in solar cells. And this is a little snapshot of the lower right-hand corner of NREL's certified efficiency chart. And you can see that the perovskite, which sits here at 26.7%, is really just on the heels of crystalline silicon, which is at 27.1% there. And if you compare this to other thin film solar technologies, CIGS or CAD-TEL, both around 23%, or organic, which there are reports in literature over 20% now, but at least the highest point on the chart here is just under 20. Really, it kind of puts them a bit to shame to have substantially higher performance metrics, at least on day 0. The issue with perovskites, and kind of what brings me here today to talk to you about, is not in their initial efficiencies, but rather in the fact that those efficiencies don't hold for an excruciatingly long period of time. For most solar technologies, you want that to hold for decade timescales, and that's indeed what silicon can do. But perovskites, the best they've demonstrated, is somewhere in the neighborhood of few thousand hours for degradation from its day 1 value to a few thousand hours, about 80% or so of that initial performance. And so when we talk about degradation, in my lab, we've looked at a bunch of different degradation reactions, and what we found is that the initiation, right, that first step, always falls into one of these 2 bins. First one being charge transfer, and I kind of put this in order of importance, so this is the first important one. The most important reaction that underscores the degradation of these systems is some kind of electrochemical or charge transfer reaction. And that's the one that I'll spend most of my time here talking to you about. And the adjacency is an amine. So lead can be reduced. You get this lead zero. There's still, I think, a lot of emphasis about lead zero in the community. I de-emphasize that because I think if you see lead zero, you've pushed your system so far beyond its limits that if that's your end state, I think you're basically clinically dead at that point. So I don't worry so much about lead reduction anymore. And I think the primary lead reductant is an amine, which is actually the product of the other main degradation reaction, which is an acid-base reaction or something involving protons. And so you have a lot of organoammoniums in these systems. If it's deprotonated, you can make an amine. And I think that's the primary then finally redox reagent for lead. But I'm not going to get into that today. The other thing that can happen with amines, and this is another adjacency, is a condensation reaction between amines and formamidinium, which also spells a lot of problems for this system structurally, because I end up making cations, like the most common one is methyl formamidinium, that are just too big to fit in that perovskite lattice, and it kind of unfolds that system, leads to substantial strain and other things. But things like strain, things like ion migration, I like to think about them as consequences of one of these two things. And so these are kind of the original sin, as it were, for halide perovskite degradation. And here's a really simple experiment that can be done in any lab. If I take a film of aluminum on a little piece of glass and I dip it in methyl ammonium iodide, nothing happens. But if I dip it in lead iodide, it gets completely corroded and it goes away in seconds. And what's behind that is an electrochemical reaction. And this is a really spontaneous one. This is an obvious one. This is the one that we first published 6-7 years ago now. Sorry, more like 8 years ago now. And so if you have an easily oxidized and strongly reductive metal like aluminum, instead of staying as pristine aluminum 0, what will happen is you'll have a metal-metal cation redox reaction with lead 2, and you will generate a lot of lead 0, and you'll generate a lot of aluminum 3 in the process, because aluminum 3 has a stronger electrochemical potential than lead 2 to lead 0. And so that's the end consequence. This is a very obvious one. This is a spontaneous one. What I'm going to talk to you mostly about today are less spontaneous, are non-spontaneous ones. These are ones that happen with the application of stress, either voltage bias or light bias. And we just published a couple of weeks ago this perspective in ACS Energy Letters. And what we're trying to do is go beyond ion migration. So ion migration is this often invoked term in the literature of perovskites, but it doesn't really get to the core and the heart of what has happened. Yes, matter moves, but what mediates the movement of matter, the movement of ions, is actually some creation somewhere and some annihilation somewhere else. And so these are usually electrochemical reactions. And so behind ion migration is some sort of electrochemical reaction, because they are the sources and the sinks of ions that end up migrating. And so here's a generic framework for a device. I have a halide perovskite in the middle. I have charge transport layers on either side. I have a metal electrode on one side, and usually I have something like a fully oxidized metal like FTO or ITO on the other side. And there are numerous things that can happen. I'm going to get into these in the slides that follow. We have potential bulk effects, things like you could have oxidation reduction reactions forming interstitial halides, forming vacancies on the one hand, or you can have reactions on the charge transport layer perovskite interface, and this could leach out iodine or iodide, which could then ultimately oxidize metals, and I can even bring metals into the picture here. And that's what we'll talk about when we talk about doping in these systems. And in order to make progress here, here's an example for the one that keeps me up at night, which is interstitial iodide. And so you have maybe a place here where you can generate interstitial iodide and halide vacancies. You could also have bulk generation. You have bulk annihilation. That's basically what's known as self-healing. Basically, these reactants, or in this case, the products of this reaction, are newly formed reactants to reform the perovskite lattice. And I can have annihilation of these vacancies and interstitials to join the lattice again. And that's all mediated by things like generation, annihilation, and mass transport, either drift or diffusion, of these interstitial ions. This is in effect the ion migration equation, but it needs to be merged with the equations of semiconductors, continuity equations, Poisson equation. And so I think to make progress, we need to define the reactions that happen, the ones that are most important, and we need to develop models that incorporate and merge these chemical reactions with well-known, well-established semiconductor physics equations. And by kind of merging these, we can make a full assessment and a full model in a mixed ionic electronic context to better understand the behavior of these semiconductors. So I'm going to show you an example of an iodide redox cycle and something that it does. And one thing that we've established in my lab is that iodide oxidation is the first thing that happens which allows for halide phase separation. So if I have a system that's now a mixture of halides, let's say a mixture of iodide and bromide, the initiating step of redistribution of this lattice is basically to create a lot of vacancies so that stuff can move around. And the thing that creates that vacancy is iodide getting oxidized, leaving the lattice, and now stuff can move about. Ion migration can happen. And this is fully reversible. You can go back and collapse to the nearly well-mixed AB mixed halide system. And so here's how it works. I have an anode and a cathode. Anode's on the left, cathode's on the right, and I have a well-mixed x equals 0.5 halide system in between. If I put an anodic potential on this, so a potential difference between the anode and cathode, as I mentioned, the first thing that we can expect is iodide can get oxidized. So holes basically oxidizing these surface, the ones on the left here, iodide atoms. They leave the lattice, they make interstitials. And now we have an interstitial an interstitial diffusive gradient that's going to cause interstitials to move to the right. We also have a field between the positive anode and the negative cathode that could also allow migration of these interstitials toward the right. So whether it's diffusion, whether it's drift, you can think about it as you will. You also now have vacancies. And these vacancies will also be able to diffuse. And those vacancies are effectively allowing bromide to net move toward the left, right? Because the left side is where iodide gets oxidized. And now I have a lot of vacancies that have moved to the right here. And the electrons can re-reduce the iodide. So this is the closed circuiting of this electrochemical cell. They can re-enter the lattice as negatively charged iodide ions. And the net result is I have an iodide-enriched cathode and a bromide-enriched anode. And if I test this experimentally, we can see if this hypothesis is true. And so we have a device here. We have nickel oxide on one side, and we have C60 BCP gold on the other side. Initially, we can see the iodide, the bromide, and the lead are all well distributed vertically in this system. And if we forward bias the system, meaning the top is cathodically biased, the bottom is anodically biased, that's my forward biased situation, you can see that the iodide, after some time here, has collected at the top, the cathode, and bromide has collected at the bottom, the anode. Lead remains well distributed, so lead has little or nothing to say about this. It's the kind of scaffold that's holding this whole thing together. If I flip the biasing, and now the top is my anode, the bottom is my cathode, you can see the reverse situation has presented itself. The bottom has become enriched in iodide, depleted at the top. The top has become enriched in bromide and depleted at the bottom. And so this kind of draws this picture of an electrochemical cell initiating by iodide redox, oxidation on one side, reduction on the other. And so this is the way we can sort of schematically draw this. We have our anodic reaction, which is iodide oxidation, and we have our cathodic reaction, which is iodide reduction, and all mediated by electrons and holes and halide vacancies on this lattice. It's a very simple closed form situation. Now, what if we do something like we change out our electrode? So instead of gold, which is a relatively decent anode in the presence of iodide, it's not readily etched by iodide. If we change it out with silver, again, we have the situation where initially our system is well mixed. Iodide and bromide and lead, they're all evenly distributed. If I forward bias this device, so silver is my cathode, then I get the same situation. Iodide is enriched at the top, bromide is enriched at the bottom. It all behaves very similar to my gold situation. But now I reverse bias the situation, and silver is now my anode. So what happens is silver is more easily oxidized than iodide. And so I have effectively interrupted the iodide redox cycle. And if I have done that, then if you believe me that iodide oxidation is at the core of halide phase separation and redistribution, then because I've interrupted iodide oxidation, I no longer have halide phase separation. And that's what I see. Iodide and bromide are all both well distributed and equal to that of the lead component. And as a consequence, I'm actually bringing silver into this system. So silver is now entering the lattice as a consequence, because something had to have gotten oxidized. And in this case, it was silver. And does anyone have a guess what got reduced? Remember I talked about doping. Who has a guess what got reduced in the process of pulling? Because remember, redox reactions, they always have to happen closed-circuited. Right? You don't just, matter doesn't like being charged. Right? That's why we have lightning, to discharge stuff. But what got reduced when I oxidized silver and brought it in? I think I heard someone mumble it. It's the perovskite. So the perovskite got N-doped. Every metal cation that enters that system, the perovskite gets N-doped. And so the final part of this talk. So I'm trying to bring it around at the end. But remember this, because this will come in and be important when we talk about reduction and doping the perovskite. Okay, so here's the situation here. When my silver is a cathode, it's just the same. I have anodic and cathodic reactions that involve iodide. But when I have silver as an anode, now instead of iodide getting oxidized, it's silver that gets oxidized. And I end up creating all of these silver interstitials, and that's what is sort of taking over when I oxidize the system. And so this is only an issue for mixed halide systems at high biases, right? Like, we don't have to worry about iodide oxidation in pure iodide systems, do we? Yeah, we do. Okay, so let's talk about it. So we definitely have to worry about it even in the absence of bromide. Here's a schematic diagram showing the kinds of things we need to be concerned about. And I just want to impress upon you, lead reduction is not in this slide, because I don't really worry about lead reduction anymore. I don't think that. I think that is not something that really is important to this system. When lead is reduced, you've pushed it way too far. And so this is taking the archetypal methylammonium lead iodide. I need to worry about at the anode. I need to worry about iodide oxidation. When I have a whole transport layer, I need to be very worried about the fact that it can react with oxidized iodide. So we'll get to that in a moment. And then the reduction reaction, I need to be worried about MA reduction, methylammonium being reduced, in which case I've destroyed the system. I'll start total destruction. But I also have to be worried about gold oxidation when I make triiodide, which I will make in a whole transport layer. Triiodide is very easy to make in a whole transport layer. And triiodide is an especially fantastic gold etchant. And so I need to be worried about gold oxidation and gold reduction at the FTO interface, where it's cathodically biased. And so let's look at the voltage bias thresholds for these different phenomena. So what I'm showing here are a little hard to read, but these are cross-sectional TOF SIMS, I don't know what you call them, spectrograms, I guess. Depth profiles, thank you, Tonio. So what I'm looking at here is the profile for gold, as well as in the dashed lines, the profile for tin, which is showing me where the FTO perovskite interface is. That's what the dashed ones are. And so the gold, what we see is that 0.6 volts, 0.7 volts. It's not enough to have any gold in the system. There's basically no gold. And then at some point, what I've done is I've effectively pile drived the gold to that gold FTO interface. But this was just the remnant of what we had scraped, what we had neglected to get off when we peeled off the gold contact. And so you see some gold that shows up here. But now when I go to 0.8 volts, 0.9 volts, 1 volt, you can start to see massive amounts of gold in this system. If I add a spiral layer on top, you can see that I need to push it a little bit higher, and that's basically because of the voltage drop on the spiral layer. But these are still shockingly low voltages, 1.3 volts, 1.2 volts, and I'm able to start getting substantial gold signals that enter this perovskite. So these very low electrochemical thresholds for gold oxidation in the presence of triiodide, which if you're oxidizing iodide, you're making triiodide. And for those that would prefer to see this in kind of a real space image, if you take a system, you can see gold entered, and then when you remove the bias, it will actually get reduced again, and you have these gold colloids that form inside the perovskite system. And it's hard to see here because we just took a little slice, but we know from XPS profiling, if you wash off all the perovskite, there's gold that has plated out at the oxide interface as well. So I mentioned about spiro, that's the well-known sort of whole transport material in perovskite solar cells. And these systems, there have been numerous observations in literature of iodine just soaking these HTMs. But what dictates this infiltration is actually the fact that when I have a shallow HOMO system like spiro, and the shallowness basically needs to be shallower than 5.4 eV, I have loads of electrons at relatively low potential, and those electrons are capable of reducing iodine and therefore getting p-doped as a result of exposure to any oxidized iodide. If I have a deep HOMO system, I don't get a lot of this infiltration because those electrons just don't exist at relatively shallow potential. And here's an example of iodine in spiro. So I want to draw your attention to the lead carbon interface here, this one between orange and blue. You can see there's a pretty abrupt interface between those two profiles, between methylammonium lead iodide and spiro. Look at how much iodine has just soaked into this system. And that's just spontaneous. Upon spinning spiro on top of an iodide perovskite, substantial amounts of iodine leaches in. And if I put a bias on this thing, go to 0.6 volts, not much happens. 0.7 volts, look at my iodine signature, it's gone up. 0.8 volts, it's gone up even more. And if I put this back in the TEM after 1 volt for 12 hours, you can see this zone of iodine infiltration has expanded. And so iodine that gets oxidized will readily enter and dope, and you make a very p-doped spiro at this interface. And as such, it kind of makes a really nice ohmic contact. So it's a great ohmic contact. But it also has its other drawbacks as well, because I now have this possible bath and source of triiodide, which is dangerous. We've measured iodine diffusion rates basically the same way that a calcium test works. So calcium is a good test for oxygen or humidity. We've basically taken the calcium test, which basically you're looking at how much time it takes for calcium to be oxidized and rendered insulating in the presence of oxygen or water, and we've just ported it over to iodine. And so silver is a good one, because silver, it doesn't care about the presence of oxygen and water, but iodine will quickly render it insulating. And so we can measure the amount of time it takes upon exposure to an iodine ambient for that silver to be decommissioned, to be rendered insulating and non-conductive. And taking two examples here, here's poly-TPD, shallow homopolymer. You can see it renders unconductive within 200 seconds. And PVK, a much deeper homopolymer, and you can see it holds on substantially longer. And you can fit these transients to understand the diffusion coefficients in these systems, or iodine permeability, as it were. And what we see is that shallow homoorganics, whether they're small molecule, whether thermally evaporated, whether they're polymers, spin-coated, anything that's shallow, you have quick diffusion of iodine. Anything that's deeper, and you have much slower diffusion. And This energy around here is what we associate to this iodine, triiodide, iodide redox couple. It's going to be somewhere in here, and that's kind of where we see massive transition from fast redox-mediated iodine transport to much slower redox-mediated iodine transport. And unfortunately, I put a gulp here, the methylammonium lead iodide or any iodide perovskites, its HOMO energy sits right here. So if I want a whole transport layer that's capable of injecting or extracting holes from the perovskite, it's also unfortunately capable of being doped by iodine and being this sort of readily mobile circuit for iodine transport. To close this picture, we can see that iodine also dopes these shallow hole transport layer organics. So we can see that the delta I, the change in current upon exposure, is huge the shallower the HOMO I have because I'm effectively doping it better, and therefore the conductivity goes up. To finally close that loop using perovskite as the iodine source, so if I have this stack here, and what I'm checking here is the conductivity of the organic bridge, we can see the same trend. So if I irradiate the perovskite and then I shut off the irradiation, what happens is I can measure the transport of the organic, which in the absence of light is way more conductive than the perovskite. The perovskite is very photoconductive, but actually in the dark, it's very insulating. And so I can actually look at the transport in the organic, and I can see the same trend. Iodine is leached out from irradiation photolysis of the perovskite, and I can see this change in conductivity in that organic whole transport layer. Okay, so I still have some time here. So what happens when iodide is oxidized? So we unfortunately figured out that there's also a catalytic cycle that can go on between iodide oxidation and the organoammonium cations in the hybrid organic-inorganic perovskites. And it goes something like this. If you have your halide perovskite, then I, at some point, will oxidize iodide. Any oxidized iodide in the presence of other lattice iodide will basically make triiodide. And unfortunately, as I'll show in the next slide, triiodide is a strong enough base to deprotonate either formamidinium or methylammonium. In the case of formamidinium, I break it down into HCN and ammonia. In the case of methylammonium, I break it down into methylamine. And the subsequent HI is the final product. And then I make HI3. This is not a very stable product. And so eventually I make HI and I2. And I2, in the presence of more iodide, I just make triiodide again. And so I have this unfortunate catalytic cycle. Only one has to happen, and it just keeps going. And yes, this one will actually make, if I do this in the presence of methylammonium, I will see lots of lead zero, and that's because of this amine, which is a reducing agent toward lead. And so you will see lead zero upon this catalytic reaction if you have methylammonium around. So here's what happens. If I have FAI and I put a little bit of iodine in the solution, I will make Fa triiodide. And that induces the formation of this type of species here, which basically forms a six-membered ring encompassing the formamidinium cation and triiodide. And in the case of methylammonium, it's effectively, in both cases, they're hydrogen bonded, very strongly hydrogen bonded. And unfortunately, so strongly that with time, this leads to the breaking of this complex into the constituent components that I showed you, this ultimate deprotonation. And unfortunately for Fa, when I deprotonate it, it's complete degradation. The products that Fa deprotonation forms cannot reform formamidinium. With methylammonium, actually, if I make methylamine and HI, there's a pretty strong push toward reforming the methylammonium. But not in the case of Fa. That's a one-way street to being degraded. So we asked the question if we could stop this cycle. And the most effective means that we saw was, could we put something here, something there that could act as an iodine reductant? So if iodide is ever oxidized, could it just interrupt it? We know there's one, silver, not a good one, because we don't want silver entering the lattice. Maybe there's another system that we could use as like this intermediate to, if any iodide is oxidized, maybe it will push it right back to iodide. And we drew inspiration from actually biochemical processes where thiols are pretty good reducing agents. And what we wanted to do was actually see if we could use thiols to reduce iodine and then make these disulfide compounds and therefore interrupt this catalytic cycle. And as one thing that I want to show you, just because it's nicely drawing out from what I showed you a few slides back, if I take a system like Spiro with an iodide perovskite, I'm showing here again that iodine can leach into the spiral layer. You see this black trace is the iodine that has really infiltrated the Spiro. And if I put this thiol between Spiro and the perovskite, you can see that the iodine and lead traces follow each other very well. And that's because it's actually holding back the iodide from being infiltrated, because it's never actually getting oxidized without being just reformed into iodide through the action of this thiol compound. It doesn't appear to compromise the performance of the systems, which is good. It might improve it, but statistically, let's just say it doesn't hurt it, which is already a good thing. And this is really just a vanishingly thin coating of this thiol compound, which we only tried 3 of them, whether this R group is methoxy or hydrogen or fluorine. It appears to sort of preserve the performance of these devices, which is great. If we look at the stability, we can see that a few of them, in particular either the fluorinated compound or the methoxy compound, are pretty good at preserving the stability even at 85 C, which some of these cross-sectional analyses show really allows iodine to permeate that spiral layer. But some of these thiols kind of hold that permeation back and therefore hold some of this degradation back as well. And I think a lot of the Spiro instabilities, thermal instabilities, I know there's been some work from Munji Buendi's group on this, I think a lot of its sources from iodine infiltrating that system and interacting with some of the other stuff in the spiral layer. So maybe one solution might be remove some of those additives. Another solution is just don't let iodine to enter it in the first place. And maybe doing both is the sort of better solution. But to my knowledge, that hasn't been attempted. What we've done is we've looked into trying to replace Spiro with other compounds. And in this case, we took this pretty well-known whole transport layer from the OLED field, and it's readily doped by moly oxide. It's also readily doped by iodine. But if we co-evaporate this compound, empty data, with moly oxide, we strongly p-dope it, and we also increase its density. And the action of sort of pre-doping it with moly oxide really holds back a lot of iodine. If you look at the Spiro system up here, you can see that the reason why it's on the top of this waterfall plot is there's so much iodine that's in that system. And you can see after annealing a lot more of it. But if I take something that holds back iodine, in this case this composite of empty data and moly oxide, you can see that it manages to keep in check the iodine in that whole transport layer. And as such, it can really withstand substantially more stress at higher temperatures. So 60 C isn't enough to do much, but 70 C is already enough to absolutely destroy the Spiro, the conventional doped Spiro system. And I think that has a lot to do with iodine oxidation and infiltration into these media. So what about doping? This is the last part of my talk here. That should be easy, right? It's just a reduction reaction. And ideally, it's an irreversible one. And this is one nagging issue, this irreversibility, because perovskites do feature ion migration. And a lot of ions will just come in and change they'll kind of be a sort of anti-correlating species to, if you want to affect change, say dope it, something else will come in and just stymie that potential reaction. And this has to do a lot with our lack of substantial success with doping perovskites in general. The way we started down this path was with using molecular oxidants. This is a well-known one, this MOLY-TFD compound, strong oxidizing agent. What we see is that putting this on the surface does in fact make a much deeper work function, but you can see the conductivity of the system is basically unchanged. And so what has happened with such a system is I'm doping it, but I'm just doping the surface. It's not doing anything to the bulk properties of the perovskite. And so the picture I can draw, and you can see the bulk, actually the XPS shows even the core levels are shifting, not just the work function, but everything is really shifting. So the system, the surface, is really getting p-type doped, but it's not infiltrating the bulk. And so it's just a surface doping. Nevertheless, you can make a really close analogy with a type of early silicon solar cell, the screen-printed aluminum BSF solar cell back surface field. And the back here is basically p-doped, and it does promote whole collections. So devices are actually aided by putting a little p-doped back surface on an NIP type structure. It's not necessarily a bad thing, but it doesn't really get to the core of true doping. So then we tried using cesium-lead bromide nanocrystals, see if we could dope those through electrochemistry. The way this works is pretty simple. You put your cesium-lead bromide nanocrystals on a surface, in this case ITO. You immerse it in an electrolyte. In this case, I think it was TEA, I forget, PF6. I can't remember the counter anion. But you inject electrons from the ITO electrode, and every time you inject an electron, you attach one of these bulky ammonium cations to the surface, and that's electrochemical doping. We were very careful not to go beyond the electrochemical stable window. In the case of cesium-lead bromide, for us, that was about minus 0.9 volts to 0.5 volts. If you push beyond it, you see all kinds of electrochemistry unfolding, and you are reducing lead. You see lead zero in the system. You are evolving bromine. So that's not a good idea. But if you stay within the stability window, you can see a sort of nicely reversible cycling. And you can get real change here. You can get work function to the tune of shifts more than half in EV. And it's also seen in the core levels, not just the work function. This is work together with Antoine Kahn, who's an expert on electron spectroscopy and doping. And you can also see changes to conductivity. So you can see about a factor of 20 increase in conductivity when I n-dope the system. And that was coming together with an increase in PL. We said, oh, this is great. This is going to allow us to make a great LED, a great laser diode. We've n-doped this system. The PL got brighter. That's great. And unfortunately, also, the lifetime got longer. And that's inconsistent with radiative recombination. If I'm doping this system, if I'm adding electrons to it, free electrons to it, my lifetime should go down when my PL goes up. But we did not see that. We saw that PL went up and lifetime also went up. And so what we suggest, it's hard to know, but what we think is that the injected electrons are actually filling traps, and our increase in conductivity is actually more or less an increase in mobility, because we're basically making the system a better electron transporter. We're not actually adding free electrons to that system. So back to square one. It's really hard to dope these systems. So we went back to this device, and we thought more about metal infiltration. And we wanted to see if every time a metal cation enters this lattice, do I actually n-dope it? Is that the other side of the redox equation? We got the aid of Lior Kronik at the Weizmann Institute in Israel. They did some density functional theory on a gold interstitial. And what they found was that the gold interstitial transition level sits somewhere in the conduction band, in other words, and right at the edge. In other words, if you do have a gold plus interstitial, it should come along for the ride with an electron. That should be the kind of stable state of a gold plus interstitial. And the system will also end up changing. The iodide transition will also go from minus to plus, and that'll come along for the ride as well. So you're going to change the interstitial population of iodide, but you'll also add electrons to the system. And that's basically coming along with the change of Fermi level will shift my interstitial population of iodide from maybe some plus, some minus to primarily minus, along with free electrons in the system. And so that's what their calculations indicated. And so we conducted these very, very simple tests. This is looking at current as a function of time for different step-ups in the voltage. And what we saw was that initially we had reasonable conduction, and we thought this was initially p-type conduction, the Fermi level that we typically measure of methylammonium lead iodide on FTO. The Fermi level sits slightly in the p-type range, and so it's consistent with some kind of p-type hole-dominated conduction initially. And then as a function of time, you can see that eventually the conduction goes down. And I go through this plateau. And we think this is where you're basically compensating that semiconductor. So had an initial hole population. Every time I inject a gold interstitial, I also inject an electron, and that is compensating the system. It's becoming basically insulating. You can see my current falls off, and then eventually my current comes back up when I achieve N-type doping. And that was consistent with the impedance analysis that we did as well. So this is what we think is happening. You have initially p-type conduction, then the system becomes compensated, and then eventually you get an N-type medium. And the photoluminescence that I show, that I'm not going to show here, also agrees with this. We get PL that sort of goes down when I enter this compensated region when bimolecular recombination is really bad, right? When I have almost no electrons or holes around. You see that low in conductivity is also associated to a low in PL. And so in conclusion, I would really encourage you to treat perovskite devices as electronic devices and electrochemical cells in order to go beyond the term ion migration and really try to understand these systems at their core. And stabilizing and doping these materials presents a major challenge. But I think if we can adopt in earnest this type of approach, I think we can make some real change and progress. With that, I'd like to thank some of the agencies that helped fund this, the Department of Energy's EERE wing, as well as the Office of Naval Research. And finally, thank you for your attention. Thank you.
Thank you, Barry. Thanks for a great talk. So we have time for a few questions. If you have questions, we have microphones. We'll pass them around. And online, if you have any questions, please type your questions.
I'm going to take you up on the second point there, the first point there, that they go way beyond ion migration. 50 years ago, I did a lot of work in alkali halides, not perovskites, but alkali halides, trying to dope them with excess halogen. And that was done principally with potassium iodide doped with iodine under extremely high pressures. And one gets the same interstitial type populations that one does with the radiation of alkali halides. And what that shows is that the iodine, in this case, binds with the anions at the anion sites and forms molecular interstitials. So your I3 minus actually is really an interstitial which is actually attached to a lattice ion, and
Yes.
it's essentially split interstitials around a lattice site.
Yes.
Also, the system generates cation and anion vacancies. And that's because of the pressure of the iodine. What happens is the interstitials actually can occupy at whatever temperature this is done at, anion and cation vacancies. It's a way of actually stabilizing that interstitial population, which leads to the formation of dislocation loops, which in fact are found in the potassium iodide, which has been heavily doped with iodine. So what I'm suggesting here is it not only goes a long way beyond ion migration, but it gets into the realm of extremely complex defect structures in ionic systems. And I think you have to be aware of this. You can try to identify the species, but you can only really understand the species of defects you have in the system, which also can lead to the transport phenomena you see. If you think about the reaction with the cations and anions and other defect populations in your perovskites, it's a very complicated system. And I resonate with your first point there, but I think it has to be done. There has to be a lot of defect spectroscopy done here to really understand what's happening in this system. It doesn't change the calculus of what, charges, transport, and so forth, but it does change the way you think about the diffusion of these defects a lot.
I'd like to pick your brain about what type of spectroscopy would be, identifying these defect levels, because they are 6-7 orders of magnitude below the sort of lattice site density.
EPR is one of them, of course, and,
Okay.
and there's been some work done with NMR, of course, as well.
I see.
I don't know if these are transparent at all, but in any wavelength between infrared and ultraviolet. And if they are, you can actually do some color center spectroscopy. But my guess is you may not be able to do that. Yeah.
Yeah, I think one of the main issues with these systems is that they tend to actually be relatively defect immune, which means non-native species or native defects don't tend to occupy electronic sites within the gap. So they tend not to be visible. And your primary excitation event is still that of the gap. And that's kind of what makes, at least in our experience, direct measurement elusive. And so we've had to turn to somewhat.
Even if they're only very close to the conduction or valence bands?
Yes.
Okay.
Yes. Yeah. And that has made, for us at least, direct measurement elusive. And then we've sort of had to just kind of interpolate it.
Okay. Good. Yeah. I have other questions. But
okay.
Questions? Okay, Barry, maybe you can comment on your choice of the thiol molecule. You mentioned you've tried two, three of them.
Tried 3.
What goes into selecting the right material?
So we worked together with Jeff Schwartz, now an emeritus faculty at chemistry, and he wanted something that was relatively thermally stable. It wouldn't be a liquid at room temperature; it'd be a solid at room temperature, and also relatively small, so that it wouldn't be this big sort of insulating monster between the transport layer and the perovskite. And we decided, and we also wanted it to be commercially available. And so we decided on these compounds as being kind of like a neat compromise. And there was also rather synthetic differences in them, like the R could be swapped out again commercially. There has since been some work. We tried alkyl thiols. Those are obviously readily commercially available, but we didn't have much success with them. We think they just make a relatively large insulating barrier, and the processing window for those to be successful might just be very small. But there was recent work from Alex Jen's group at Hong Kong where they found a thiol that I think works better than the one that we showed, and they ascribe the success to a similar thing. It kind of mediates iodide oxidation, sort of interrupts it. I would say it reduces it back, and we haven't tried that one in our lab, but I'd be curious to attempt that one, because the catalog of thiols is enormous. And so it's very challenging to try to identify which one to use.
Great. Any questions from the audience? Trace, any questions online? Okay. If not, we do have a reception. Let's thank Professor Rand again.
Thank you all.
Thank you, Barry. So we're going to have a reception, so please stay back, and Professor Rand will be here to answer any questions you have or if you want to talk one-on-one.